Hello everyone. Welcome to the video presentation of our Chemical and Biological Engineering Senior Design Project. Our project is called Waste Not, Want Not, turning Fort Collins food waste into fuel. And we will be doing that through a process called hydrothermal liquefaction. First, let's look at the motivation for this project. The U.S. Department of Energy is investing funds into the research and development of a hydrothermal liquefaction process to convert wet biomass such as food waste into fuel. The city of Fort Collins is considering alternative methods of food waste disposal in an effort to reduce the amount of food waste in Larimer County landfill. The city of Fort Collins also has a plan called the Road to Zero Waste Plan. The goal of this is to have the city produce zero waste by the year 2030, and one of the main aspects of that plan is to find a way to convert waste into energy. Well, hydrothermal liquefaction of food waste is the answer to all of these questions.
The HTL and upgrading process will develop a stable biofuel that can be sold and further refined into a usable product. Modeling the process will also provide a generalized understanding of the economics and sustainability of the system.
The overall goal of this project was to engineer a feasible reaction that would convert food waste to bio-oil. The benefits of this are that it reduces the amount of food waste in Fort Collins landfills and provides alternatives to crude oil. In order to engineer this reaction, we first researched hydrothermal liquefaction, including chemical catalysts needed, the chemical mechanisms, and possible reactants. Next, we created a detailed process simulation in Aspen Plus. Third, we analyzed the process life cycle, sustainability, and economics to determine the overall feasibility and to make recommendations on how to improve the product.
For the process analysis method and tools that were used in this project, we have Excel sheets where we analyze the chemical to build a table comparing the material that could be used for the feedstock. And then we used Draw.io app to build a flowsheet diagram comparing the different routes that this project could take. And then Aspen Plus was used to model and simulate a process for the HTL process. Excel sheets will also be used in the economical analysis to compare the prices and material for the material and the equipment per year. Lastly, for the life cycle analysis, OpenLCA will be used in the future.
The history of hydrothermal liquefaction is brief. Research first began in the early 1970s during an oil embargo at the Pittsburgh Energy Research Center. They were able to produce around 5,000 kilograms of oil before the process was halted due to problems with undissolved solids. Lawrence Berkeley Laboratory was also doing research around the same time, and their process was halted after the oil prices stabilized. Both of these laboratories used wood chips as their feedstock, but had very different processing conditions, and as such, their yields varied wildly. This was before the optimal processing conditions were known. Most of the research on hydrothermal liquefaction has been accomplished in the last 20 years, with National Renewable Energy Lab and Pacific Northwest National Laboratory leading the way.
The U.S. Energy Information Administration forecasts an increase in the consumption of gasoline this summer relative to summer 2020 and a net increase in the consumption of gasoline through the year 2050, as seen in the chart in the bottom left. Since both crude and bio-oil are used in the production of gasoline and other transportation fuels, this sustained demand for gasoline should keep the demand for oil high. Predicting the supply of crude oil is difficult, as it depends on a complex mixture of international diplomacy and trade, as well as United States domestic policy decisions. As seen in the figure on the bottom right, there are a variety of predictions for the future of United States crude oil production. Since bio-oil directly competes with crude oil, the supply of crude oil will have a large effect on the demand for bio-oil.
When considering recycling food waste, there are several options available. In the City of Fort Collins' Road to Zero Waste plan, they include anaerobic digestion and composting as possible technologies to include. These will be discussed in more depth in the following slides. Here, hydrothermal liquefaction is recommended due to several key advantages. Firstly, HTL can process wet biomass, bypassing the need for expensive and time-consuming drying processes. Additionally, the HTL process actually sanitizes the biomass, thereby eliminating potentially harmful pathogens that are not eliminated in composting methods. Finally, the HTL process is more easily able to be controlled and fine-tuned since parameters such as temperature and pressure can be controlled.
One of the alternatives to hydrothermal liquefaction is called anaerobic digestion. This is a process in which bacteria are used to break down organic material to produce biogas. Biogas is just a mixture of methane and other greenhouse gases, and it can be captured and used as an energy source. Some of the advantages of anaerobic digestion: food waste has a very high potential for biogas, and the energy produced by biogas exceeds the energy that's used to fuel it, so the excess can be captured and sold. However, there are obviously some disadvantages with anaerobic digestion. The first is that the biogas is not pure methane, so if it was to be used as a natural gas replacement, it would have to be purified, which not only reduced the yield, could also risk introducing impurities into the gas, making it less marketable. And it requires a large area of land to implement the process, which is obviously not environmentally favorable.
Composting is a method of recycling biomass, usually to be processed into fertilizer. Composting is simple and easy to conduct on large or small scales, and the fertilizer produced can be sold. However, the use of the fertilizer that is produced poses a threat of eutrophication, or excessive buildup of nutrients in nearby bodies of water. Composting also requires environmentally unfavorable land usage and does not sanitize the feedstock, as HTL would.
Because bio-oil is less energy dense than crude oil, it has to be sold at a comparatively lower price. As seen in the figure, oil prices have historically been volatile, so there is a large range of projected prices in upcoming years. Lower oil prices make bio-oil harder to price competitively. So in the case of a high price or a reference price case, it is much more likely that bio-oil will be able to be competitive on the market than it is if oil prices continue to stay low.
Moving on to the development of the process flow sheet as seen to the left was followed. Information regarding the decisions for each step of the model will be detailed in the coming slides.
When considering using food waste as a feedstock for chemical processing, it's important to realize that food waste is a complex and mostly unpredictable mixture of dozens of chemical components. Studies that use food waste as a feedstock generally don't use a trash bin full of biomass, but rather one or a few specific food waste items. The process described here is intended to accept mixed feedstock of varying compositions, so generalized compositions were used here to simplify the model.
The first thing that we had to consider when designing the reactor for the hydrothermal liquefaction process is whether to have a batch or a continuous process. Batch processes are rarely used in industrial applications, as they simply cannot make as much product as continuous reactors in the same amount of time due to the loading and unloading times. This is especially disadvantageous in fuel production, where large volumes need to be produced every day. So with that in mind, we decided to go with the continuous process. Now we had to decide which type of reactor we were going to use. Our options were a plug flow reactor, a continuous stirred tank reactor in series with a plug flow reactor, and a catalytic reactor. The plug flow reactor seems like a good choice at first, as all the reactor contents are well mixed and the biomass flows through these long narrow tubes, decreasing the total area required for the reactor. However, with these long tubes, biomass has a tendency to get stuck, leading to a phenomenon called plugging. The way to solve this plugging issue is to have a continuous stirred tank reactor in series with the plug flow reactor. This is going to reduce the length that the plug flow reactor tubes need to be, while also maintaining the residence time, or the time that the biomass spends in the reactor. However, a continuous stirred tank reactor with the specifications needed for these reactions would be very expensive. The final option is a catalytic reactor. This is a reactor in which catalyst is loaded into the reactor before the process is started, so that when the biomass flows into the reactor, it's in contact with the catalyst, which increases the yield and the rate of reaction for this process. So for those reasons, we decided to go with a catalytic reactor.
During the HTL reaction, an amount of the carbon-based product tends to partition into the aqueous phase instead of staying in the bio-oil phase, thus reducing the overall yield. This can be lessened by introducing a catalyst into the reactor. Homogeneous catalysts such as CEZROX provide the best overall yield and are easier to recycle and reuse. The HTL process provides a product stream containing a mixture of gaseous product, aqueous product, undesired solids, and the desired bio-oil product. This necessitates at least 3 different types of separation. First, removal of undesired solids through filtering. removal of gaseous byproduct through flash distillation, and then separation of the aqueous and bio-oil phases through methods such as liquid-lipid extraction or use of a decanter. Following separations, the bio-oil is still not stable enough for transportation, meaning some amount of upgrading is necessary. A hydrotreating process could be implemented to remove excess molecules and remove unstable double and triple bonds present in the product.
Here's a block diagram of our general process. We have feedstock and water at the beginning being fed into the hydrothermal liquefaction reactor. The effluent of the reactor is then fed into the separation processes block. This block separates the wanted product from the unwanted product. The gaseous byproduct and solid residue byproduct can then be fed into a combustion block, which will generate heat that can be resupplied to the reactor to keep the reactor at the set temperature. After the separation process, the wanted products go into the upgrading phase. We need to upgrade the oil because at its current state, it's not stable enough to be transported. So the first stage of the upgrading is called hydrotreatment. After hydrotreatment, the oil is fed into a flash distillation unit, which separates the unwanted products from the wanted products, and out comes the upgraded bio-oil.
In the next set of slides, we will discuss the key elements present in the hydrothermal liquefaction portion of the process model.
Because the exact composition of food waste is impossible to predict, a very simple approximation was used based on data for sugarcane waste scraps. It is intended that the process parameters such as temperature and pressure be adjusted once the food waste compositions are more defined.
Here's an in-depth look at the reactor that we use for the HTL process. We decided to go with a fluidized bed catalytic reactor that operates at 300 degrees Celsius, a pressure of 15 megapascals, and a residence time of 30 minutes. We modeled it as an R yield reactor in Aspen Plus because it allowed us to manually enter the yields for each product. And yields were interpolated from our data sources. We assume that there is a 100% conversion of biomass to products in this process. We were able to achieve an effluent stream with a biocrude oil weight percent of 44.
For the process heating, the heat exchangers, denoted HX1 and HX2, were set so that they were countercurrent in flow and assumed to be the shortcut model provided in Aspen Plus. HX1 was modeled so that the hot stream outlet temperature would be set to 125 degrees Celsius, while HX2 would have a cold stream outlet temperature of 300 degrees Celsius. When modeling the furnace, an R-stoic reactor was used to allow for the combustion reactions based off of the feed materials to be automatically generated. The furnace was operated at 400 degrees Celsius and 15 megapascals, and a design spec was added so that the stream leaving the furnace would contain 5% oxygen by weight. This ensured that the oxygen supplied to the furnace was in excess.
The separation stage consists of a flash distillation unit to remove excess gaseous product and a decanter to separate the undesired aqueous phase products from the bio-oil. Both units are run between 80 and 90 degrees Celsius and at 1 atm. While other methods of separation may provide better product yield, this method was chosen for model simplicity. Following the HTL process, the bio-oil is sent to the upgrading phase. First, the product is fed through a pump in order to achieve the high pressure necessary for the hydrotreating process. Next, the product is mixed with a hydrogen feed stream and hydrogen recycle stream. This is so hydrogen remains the non-limiting reactant in the following reaction. After going through the hydrotreating process in the reactor labeled HT, the product is cooled, then mixed with a water recycle stream before being fed into a 3-outlet flash distillation unit. This block separates the product stream into a hydrogen recycle stream, a water stream, and the desired product stream. The water stream is then separated using a splitter into a wastewater stream and a water recycle stream. The hydrotreating reactor combines the bio-oil product stream with excess hydrogen gas at 400 degrees Celsius and 0.85 megapascals. Reactions were written as shown and each assumed 100% conversion of the limiting reactant. In order to meet this requirement, a hydrogen feed stream was introduced rather than relying solely on the hydrogen recycle stream. The flow rate of this feed stream was systematically altered in order to reach a target mass fraction of hydrogen exiting the reactor. This was done to minimize the amount of hydrogen being introduced into the system.
Moving forward with this project, several considerations need to be made. For the feedstock, we would have to determine a separate collection method for feedstock alone, whether that be commercial or residential or a combination of the two, separate from regular waste. In terms of the reactor conditions such as temperature and residence time would need to be experimented with and more precise yield data would need to be determined in order to provide a better yield of our desired products. In terms of the process heating, a better way to model the furnace than the R-stoic reactor would need to be determined. Moving on to the separations of the process, introducing different separation techniques following the flash distillation column, including a liquid-liquid extractor, would be advised. In addition, adding a recovery process following the decanter would allow for more of the desired products to be re-added into the stream. Lastly, for the upgrading process, implementing a hydrogen regeneration process would allow for the removal of the hydrogen feed being introduced to the upgrading process and allow for less buildup of hydrogen gas in the recycle stream. Additionally, the utility requirements for this process can be reconsidered and potentially reduced.